All right, today, hey, can we close that, please? All right. Today, let's take a few notes on the graphing of the sine function. My goal today, I want to do kind of some new types today, where we throw in some fractions, we throw in some other stuff. Caddy, where's mine? All right. So, all right. But let's go through a couple examples here of when we throw in negatives or we throw in some new stuff. So I have two examples that will be kind of a refresher, and then we have a brand new thing that I want to show you today. All right, so here we go. So we're in section 4.5. 4.5. All right. And we're graphing the trig function.
Actually, I can look for you. I can look. Pretty sure.
Oh my gosh, Sam, I love you.
Okay, hey. All right, so here we go. The first thing, we're going to be talking about the sine function today. Now, if we get a little bit of a chance today, because I know we're kind of on a shortened period today, I want to do two examples of problems we did yesterday, kind of one easy one kind of more difficult one. But I want to show you kind of the stuff we haven't seen yet. And then we have a brand new type where we're going to talk about shifting today, where we're going to talk about the hard material for shifting. Like we did the top, like up and down shifting, that's considered easy. That's the type I would assign to you today. But there's a new type of shifting that we're going to save for later this week. But the new thing I want to get to today, like the brand new stuff, is I want to graph the cosecant function, which is the reciprocal function of sine, which is very, very different. And the reason why I want to do that today is so we can compare it to one of these examples I'm going to do, so you can see the differences. So we're going to try to do at least one example of this today. Not two, we'll try to do just at least one. Okay? And I'll try to show you the ropes, and I'll try to explain the best of my ability why you get that answer. All right, questions?
No.
Great.
How's your day?
All right, let's go through the first couple examples here. Let's do the sine function here, but let's kind of do a new twist on it. So my first example, let's go with
7.
Let's go with f of x.
13.
Let's go 7 sine
13.
1 over 13x.
Ooh.
So this is new. We're throwing in a fraction now.
Ooh.
Okay, now the number I'm throwing in, the 7 is affecting my amplitude. It looks like we're not shifting this thing up or down any, so we're going to be over the origin, the x-axis. But the 1 over 13 will affect the period length, the frequency of it. So traditionally, this is the formula that we use for when we graph trig functions. That's like the generic formula for it, where A affects amplitude, C affects the shift, where this is this shifts your origin, which is a shift of some form. We'll talk about that. This affects amplitude. That's the height of the waves. And the B affects the period or frequency of it. And that basically what the period affects is those 4 hash marks going across. Okay? But this is kind of the weird one today that I want to talk about. This is kind of something new we haven't seen yet. So on this particular problem, I know that if I graph this, we're still over the major axis, but now I'm going to hit a peak of 7 and negative 7. Because that's the number up front, that's how tall the waves are, from the origin line. So if we're going to shift that thing, we have to think about where that height is from the origin. Okay? Alright, now, the 4 hash marks going across. What does it usually go out to?
It goes to
2 pi.
2 pi. That's usually what I go out to. That's like that's one period. That's 360, by the way.
3 pi half.
But what we have to do is we are affecting the period. We have to divide by the number that's in front of the x. So my number, I'm dividing by a 1 over 13.
We're just multiplying.
Exactly. We have to flip it over. So my answer is 26 pi.
Wow, that's a big piece of.
That's a big picture, right? That is the last marker down the road. Whatever the number is in front of your x, you always divide by it. And that's the 4th marker down the road. So that is 26 pi. Now, to get to the other ones, we cut that in half, which is 13 pi, we cut that in half again, which is 13 pi over 2, because I can't actually cut that in half without getting
7
a
and a half
decimal.
pies.
Yeah, I wouldn't want to do that. 6.5, you mean, 6.5.
Oh, that's what I meant, my
Um,
bad, sorry.
And then the next one is I multiply it by 3, which is 39 pi over 2. Because you multiply this one by 3 to get to the third mark.
Oh.
Okay, so it's half, multiplied by 3.
We did.
Okay, we're good so far. Okay, now, to draw this is a normal sine function, so we start at the origin, go to the tallest point, come back to 0, go to the lowest point, come back to 0. This is the sine function. Now, again, I'm just drawing one picture. This thing would continue to go up and down for the next, 4 markers, and then going this way would continue to go. And how I'd figure out what those other markers are if I had to keep extending, I would use this 13 pi over 2 and add that to this one.
Oh my.
And that's how you get those markers. Then add another 13 pi over 2. Add
Why
another
would we ever want to
Because
do
that's,
that?
that's what we're doing. 13 pi over 2 is actually the spacing perfectly. So,
Wait, why would we want to?
if the picture, like the book, I'm not going to have you do this, Dave, but if the book ever asks you to draw 2 period lengths or 3, I know I had to do that a lot in college. They said draw 3 period lengths, at least 2 of them in the positive and 1 in the negative. So, okay, so I would extend
So it'd be
past,
negative
so I'd go 4 or 5 more hash marks to draw the next picture. Then I'd go a couple hash marks back this direction so I could draw that
Wouldn't the
picture.
other way be easier to just make them negative?
No, but you can't just go negative. You have to actually I know that they are negative, but you would have to actually subtract 13 pi over 2 every single time. So if it's perfectly balanced, yeah, you're right. It would turn out to be negatives. But the problem is when we start shifting, that may not be the case. And that's the thing we're going to talk about today. We're going to actually shift it right and left. For the most part, yeah, you'd be right. We'd go the other direction, about the same markers.
Yeah.
Okay, questions about these so far?
No.
Okay, that's kind of one we did yesterday. I just threw in a fraction there. We didn't really see a fraction yesterday. Now, if the fraction was out front, that's just how tall it is. We don't really have to do any weird math with it. If it's like a half out front, this is half, this is negative half. It's just how tall the waves are. They're not really tall. This one's really tall. Now, the one thing I do want to talk about though, what if it's negative? What if they had a negative sign here?
You flip it.
Yeah,
The wave is
the
going
picture
backwards.
flips over. It's reflected over the x-axis.
So we go down instead of.
So yeah, so instead of going up, my picture would go down to the lowest point, back to 0, to the tallest point, back to 0. This is what it would look like. Again, I'll make it a dashed line. But that's what it would look like if they threw in a negative. You just go the opposite direction to start with. But it uses the same pattern. Okay? Now, here's the thing. By putting a negative out front, that is not the reciprocal. It just happens to flip the picture over. That isn't giving you reciprocal answers. So kind of keep that in mind. All right. Questions about this problem? Okay. New thing today. So those are my my major examples I want to talk about. Shifting. The shifting type of problems is brand new. And this is the part that I want to talk about because I hinted at how to shift, but there was something that I didn't talk about. Is when we do the vertical shift, it's fine. We just figure out where the new origin line is and we go off of that. What if we have to do a right and left shift?
You don't.
It's really different. So let's go through an example here. All right. Okay, so new example here. Let's do one where we have to actually horizontally shift it. So let's go sine 3x plus 4. In fact, I'm going to go let's go 3 pi x plus 4. Just to throw in some weird stuff in front of the x. Okay, now.
Wait, how far does the calculator guesstimate pi to be?
8, 9 decimal places. I think it just depends on what type of calculator you have. Some can go further. Just if you have the ability, you can hit the over to actually scroll. I think my graphical one goes about 9. It sets like that's the max it will approximate it to. All right. Now, on this problem, we're not shifting it up and down. How I know the difference? Do you agree that plus 4 is on the inside of the parenthesis?
Yeah.
That means we're shifting it right and left. Okay? Everything else is the same. It still has an amplitude. We still have an up and down shift, which we're not shifting in this case because they're adding 0. But on this case, my period length is affected because the number on the inside is affected, and it's also affecting the shift, because if they add a number on the inside,
Oh my.
like that, or subtract a number, this also affects the shift, which would be a right or left shift. Now, I will try to show you the best way that I've learned how to do this over the years, and then if you need to, you can always look at the book. They kind of explain it, I just don't like the way that your book, this textbook, explains it, so I'll kind of show you what I've learned over the years of doing this. Alright, so, this is a normal sign, the only thing we're really affecting is period shifting, I'm not affecting amplitude or anything like that. So if we're going to draw a generic picture, we're going to hit 1 and -1 for amplitude. But, to affect period, normally we go out to 2 pi, right? That's the fourth hash mark down the road. What we have to do first is we have to divide by this number that's in front of the x first. It's like normal. So what's the number in front of my x?
3 pi.
3 pi. We divide by that. Even though I know there's a 4 in there, we only divide by the number that's in front of the x. So this simplifies to be 2/3. Okay, that's what it simplifies. Now, in a normal situation, that would be the fourth hash mark down the road. It would be the 2/3. So if I were to draw a generic picture, again, don't draw this, I'm just showing you, that would be the fourth hash mark down the road. That would be 2/3. Whatever you divide by, that's the fourth mark, right? Then you would cut that in half, which would be 1/3, but you put a 2 on the bottom, that's 2/6, which simplifies. You put another 2 on the bottom, and then you multiply that by 3. Okay? Again, I'm simplifying as I go, apologies, I'm kind of going through that quick. You cut in half, which you put a 2 on the bottom, that's why it's 2/6, simplifies to 1/3. Cut in half again, you multiply by 3, 3/6 is half.
Yep.
Alright, now the reason why I do that, that's what it would be if it was normal. Like if they didn't have the +4 there, that's how you do it, and you draw your sine function. But we have a +4. So now, instead of just having these markers, now these markers are moving, okay, in a certain direction. We have to figure out where they're going. So the numbers will change. And I know that some people are like, well, how do you know what the numbers are going to be? Because you're moving them now. It's not going to be 1/6, it's not going to be 1/3 on the x-axis. Where is it going? That's what we have to figure out. This number that you're looking at right here, this number is the most important number you need. So when I do horizontal shifting, this is my little trick. When I do horizontal shifting, like right and left, I actually want to find that number. So I always draw this picture. Even though I told you not to, I actually draw like a mock picture off to the side because I need to figure out what the first marker is. The first marker in a normal situation would be 1/6. That's the spacing that you're going to use for every hash mark. They're always going to be 1/6 apart. That's why we needed it. Because I know, like if I add a 1/6 to a 1/6, if I add this again, it will give me 1/3. If I add another 1/6, it will give me half. If I add another 1/6, it will give me 2/3. That's what you get when you add the fractions together. And again, you have to know how to add fractions. But why this is important? Because we're not on 0, 0. We're not starting at 0, 0. We're going to start at where this thing is the new 0. You actually set this equal to 0, and that's where you start. So the new starting point is not going to be at 0, 0 anymore. We would subtract the 4 over. You would divide by 3 pi. This, whatever that decimal is on your calculator, that's the new spot where my graph is going to start. It's going to be ugly. I know it's going to be. Half the problems we do when we shift are just super, super ugly problems. Okay?
So don't do them.
Does that make sense? Okay, now again, if you actually had a calculator, I would actually want to figure out what -4 divided by 3 pi is. And again, you'd have to put 3 pi in parentheses so that you actually get the right number. Because if you don't put it in parentheses, you won't do it right. But again, what is this number roughly? I'm expecting it to be less than 1, -1.
Negative 0.424413182.
Okay, so roughly 0.42, negative 0.42. So that means I'm on the negative side of the x-axis. That's roughly, and again, I'm not going to actually write that number down, I just want you to see what that number is if you type it in the calculator. So that means my graph, if I actually draw a mock picture here, let me get rid of this, let me get rid of our outline here. If we're going to graph this, that means I'm actually starting over here at -4 over 3 pi, and that's negative 0.42. Okay. And then to find the next hash mark, because that's my starting point, that's where 0, 0 is. So if I was drawing the sign, this is what it would look like, right? it would do the normal thing. I need to figure out where the next few hash marks are, because I don't know where they're at. There's 4 hash marks. This is the starting point. So I have to go 4 hash marks across. How I figure out the 4 hash marks? You have to take this one and add 1/6 to it. That's the number I said. That's the spacing from every hash mark. So if you add 1/6 to this, that'll be the next hash mark. Now, I don't know what 1 divided by 6 is. Can we type that in? What's 1/6?
1/6.
1 divided by 6. What is that decimal roughly?
That is 0.16666.
0.166. So it's really small, right? 0.1666. So the idea is that 0.166 is like, if you were to add 0.1666 to a negative 0.42, you're still in the negative. You're still in the negative. So my first hash marker is here. Whatever this number turned out to be.
0.25.
Yeah, 0.25. And then you'd have to add another point, so whatever this number is, 0.25, that's what you just said, you'd have to add another 1/6 to it. And you're still in the negative. So it would be coming down then.
Boom. 0.0.
Yeah, and that's where the calculator comes in handy. Now, do you see that this is super, super, super ugly when you shift? Because I'm getting weird decimals. I'm not even writing down the exact hash marks, like where they're going. And then, that's point something. I would move across, and I think it eventually gets across the x-axis now.
Did it get after the following?
And then I would have to add it again to get back to 0. And that's the normal sine graph. But again, knowing what this number was, negative 0.42, and adding a 1/6 to it, gets me to all the hash marks. Horizontal shifts are the ugliest thing in trig. They don't work out nice and pretty, as you can tell. In fact, if I wanted exact answers, I would actually have to get common denominators and add these together, and it won't look pretty. That's why using a calculator actually helps me guesstimate where they're going to be. But that is not something I would assign to you. It's too difficult. I just want you to see it, because if you've never seen it before and you went to an upper level pre-calc or a calc class in college, that's kind of an everyday problem. They just all right, horizontal shift on this problem, horizontal shift over here. They're ugly numbers, and you would have to get common denominators and figure out the actual hash marks. So I had to show you. It's one of those things you have to see it at least once.
There's only a phone call on 701.
But the thing I would expect you to be able to do: amplitude, affect normal period, the 4 normal hash marks, and shift it up and down. That's the type of thing I would expect. So do you guys agree this is kind of ugly? Okay. All right. You do have homework today. We do have homework. Now, as I said the other day, I'm assigning 3 problems. 3. The 3 problems I'm going to assign, I'm going to put them on the board here in a second. We'll talk about cosecant here in a little while. But the 3 problems I assigned, they are due this Friday, but we're going to add more tomorrow, and we're going to add some on Friday. We're going to add kind of 3 problems each day of the main trig functions. Okay, so we're going to try to do cosine tomorrow, we're going to try to do tangent on Friday. And so that way you can see now. If we have a little bit of time today, I'll show you the reciprocals. But for right now, I just want to keep it the main trig function, so we're not getting super, super confused. Okay, I was going to try to do cosecant, but I don't want to. All right, so here's your homework today. And again, I'm giving you no horizontal shifts. So, all right, here we go. Three problems. Page 533. Number 4, 10, and 60. They're kind of a different range of problems. They're just sine functions, that's it. It's just a sine function. There's no horizontal shifting. I think the first problem, they affect amplitude. The second problem affects amplitude and the period, the 4 hash marks. The third problem, 60, affects you have to shift it up and down first, then affect the period, and then affect amplitude from there. So that will have all the numbers. So it's kind of a range. There will be one of them that's negative, I believe. So just be careful that graph flips over. Okay?
Mr. Ward, what did SpaceX do yesterday?
They launched a rocket, and actually 2 rockets, and then they landed them again.
Wait, I thought one's still in, or no?
So they launched both, and then they landed 2 of them. One of them got damaged during launch. It scraped up against one of the pillars when it was launching off the launch pad. So I don't think they can reuse it, but it's the first, it's not the first time, but it's the first time that they've used a major, like Class A rocket to like launch it and land it perfectly without having it being destroyed. So they can reuse it. Because that's what NASA wants to do. They don't want to like scrap the metal anymore.
Yeah.
They want to try to reuse rockets over and over and over to save cost.
I thought they put something into
Yeah, aren't
orbit.
they sent to Mars? Wasn't that-
Mars,
Well,
yeah.
that's the overall goal. Like Elon wants to get to Mars, I think before
It's Tesla on there.
2025 or something like that. And his first thing he's gonna do, this is silly, he's gonna put a Tesla,
I thought they did
a
that.
roadster.
That
He's-
went.
Is that one of the third, is that the third rocket he launched
Yeah, I
yesterday?
think it's two- yeah, they
Okay,
did
two of
that.
them he launched and they landed.
They did that.
Then the third one was the launch where he's putting, yeah,
Because there's like a,
yeah,
they put
he's
like a
putting
dummy
a car
on
in
it.
orbit around Mars.
Because they put a
That's
dummy on the,
awesome.
they put
And
a
it's,
dummy on
and it's not in a capsule, it's just the car, and it's now a permanent satellite around Mars now.
That is so cool.
It's it has some David Bowie song or something. that
Yeah, and it's
constantly
playing
happens.
on the radio, it's got the David Bowie song Space Odyssey, and it's gonna play for the next like million years or something like that.
How does the battery die?
Because the batteries are so big in that actual car, that if it's
But-
just radio, it can last like a billion years or something like that, just continuously playing.
That's awesome.
So, it's something stupid like that,
Oh, sure, there's
but the question yesterday was, if he actually does it, which I guess he did. If he actually does it, will the car still run if they land it?
Well, I bet it would.
But it would be filled with radiation. So would the batteries eventually implode?
Hey Lauren, page 543. It's on, well, because there's no number 4 on 543. Now there is. Oh, I'm not even on
Wait, Lauren.
RIP. No,
Or
let's
how do land or like how do like rovers work?
Maybe.
Like, yeah, but like,
But that one is still shut.
don't